Question 1 deals with looking at lattice energies, and remember that lattice energy, E lat, is proportional to Q1, Q2 over D. So you're looking for things that have high charges on them, and if you consider these elements and their position in the periodic table, you'll notice that Kf is an example of a 1 plus 1 minus, CaO is 2 plus 2 minus, and scandium nitride is 3 plus 3 minus. So you're going to expect a much higher lattice energy for scandium nitride over calcium oxide over potassium fluoride. So the correct order here is C. The next one asks about 3 different interhalogen complexes. This is just a compound made up of 2 different halogens, or group 17 elements. And if you look at the shapes of these things, ICl looks like this. ICl3 is T-shaped. So we have 2 lone pairs on that central iodine, and finally ICl5 has the shape of a square pyramid. With a lone pair in one of the positions. So it's based on an octahedron. So all of these actually have molecular dipoles. Remember that we start at the positive end and go towards the negative end, so the dipole in this case points in this direction. Here these two cancel out, so the dipole points downwards, and finally the 4 in this plane here all cancel each other out, and you're just left with the same molecular dipole as we had in ICl. Okay, so all of these have net molecular dipoles. The answer is B. You next have to draw a Lewis structure for the perchlorite ion, ClO4-, that contains only single bonds. Now, I'm not going to go through the whole process of drawing these Lewis structures. I expect you to be able to do that by now. So let's just have a quick look at what it ends up looking like. We have a chlorine with 4 oxygens, and those oxygens will all have 3 non-bonding pairs of electrons, and so the overall charge of this needs to balance out to 1 minus. But to work out the formal charge, when you just draw the single bonds, and you'll see that chlorine here has an octet of atoms, so this is a satisfactory Lewis structure, as does of course all the oxygens around the outside. So the formal charge you end up with, remember that chlorine has 7 electrons, and it only has 4 electrons currently assigned to it. So the charge overall is 7 minus 4 gives you 3 plus. And this makes sense because if you look at all the oxygens, oxygen has just 6 valence electrons, and yet each of them have 7 valence electrons associated with them. So we have a 3 plus in the middle and 1 minus around the outside. And of course 4 minus plus 3 is 1 minus, so that makes sense, and so the answer here is E. The next question asks about dipole moment and which of these statements is correct. So when you're planning out an answer like this, you should have a look and see what the dipole moment is, and if you go to your data sheet, you'll find that mu equals QR. And so it is indeed given in dBi. That's the unit of the dipole moment. It is clearly proportional to charge, because you'll notice that this is exactly equal to the charge multiplied by the radius. So it's also directly proportional to the radius. It is a vector quantity, so when you draw a dipole moment, you need to indicate the direction. And the next 2 questions, clearly one of the answers is here, because they are diametrically opposed to one another. Because the first one says polar molecules have large values of dipole moment, and the next one says a polar diatomic molecule will have a 0 dipole moment. Clearly both of those cannot be true. So a polar molecule can be diatomic or any kind of shape. So a good example of that would be something like HF, that's a polar diatomic molecule. It certainly does not have a zero dipole moment, it has a large dipole moment pointing towards the fluorine. So the answer here is D. Next up is a question about electronegativities. So the main thing you have to remember here is how electronegativity changes across the periodic table. And the key thing to remember here is that fluorine is the most electronegative element, and all other elements are lower, pointing toward the opposite corner of the periodic table. So if you go to your data sheet and consult where all those elements are, you'll find that chlorine is here, and carbon is here, and germanium is here. And so the order is fluorine first, then chlorine, then carbon, then germanium. So B is the correct answer in this case. The next question expects you to know something about hybridized orbitals, and it gives you a relatively simple molecule here. This is propine. If you look at the carbon atoms, you'll see this one here is hybridized sp3. All I'm doing here is counting electron domains. This one is sp, and this one is also sp. 2 electron domains, 2 electron domains, 4 electron domains. And all you need to do here is just count the total number of orbitals we've got here. So of course there are 4 hybrid atomic orbitals make up an sp3 hybridized atom, and only 2 for each of the sp. So in total we have 8 orbitals. So the correct answer is D. Okay, which of the following statements is correct? Bonding electrons and metals are free to move from one bonding region to another. Or the electron C model explains the trends and melting points for the transition metals. The energy gap between bonding and anti-bonding molecular orbitals is largest for an insulator, and there are no anti-bonding molecular orbitals from a semiconductor. So certainly bonding electrons can be free to move from one bonding region to another, depending on the band structure. The electron C model, one of the weaknesses of it actually is that it doesn't explain that trend. So this one's okay, that one's no good. The energy gap between bonding and anti-bonding molecular orbitals is largest for an insulator. That's true. So if you look at the band structure for an insulator, it looks something like this, with a large band gap here. So that's okay. There are no anti-bonding molecular orbitals for a semiconductor. Well, there certainly are. There are always anti-bonding molecular orbitals, and so that is not true. So here we end up with answer B. Okay, which of these molecules contain a central atom that violates the octet rule? So the first thing you could possibly do here is just go through and look to see if any of them have an odd number of electrons, but it turns out in this case they don't. So for the remainder, you can draw reasonable structures for all of them as it happens, except for BH3, because there's no way you have enough electrons to complete the octet on the boron. You just have 3 electrons from the boron, 3 electrons from the hydrogen. That's 6 in total, which is not enough to complete the octet. So that's answer B. When you have a molecule with the general formula AB2, there's 2 possible shapes. You can have it either linear with 2 electron domains, or you can have it bent. And it doesn't actually matter whether it's bent because you have it based on a trigonal planar geometry like so, or whether it's bent because it's based on a tetrahedral geometry like so. Both of those are still bent. So in each case, linear or bent are the only possible options. Clearly trigonal planar T-shaped are not possible simply because you don't have enough atoms involved. The next question, assuming that the octet rule applies to all structures, which of these molecules has a non-zero formal charge on carbon? So if you go through here, you'll notice in this case you have carbon with 4 bonds, another carbon with 4 bonds. In each case of that you have a 0 formal charge. In HCN, that carbon has 4 bonds and the nitrogen has 3. Let me just draw it out. And so that's also fine. The final structure that you come up with is for CO, and CO is isoelectronic with N2, so it has the Lewis structure CO, like so. And because you only have 3 bonds to carbon and 3 bonds to oxygen, neither of them have a zero formal charge. The carbon in this case is minus and the oxygen is plus, and so the answer here is CO. So in this polar covalent bond, carbon-chlorine, the electrons in the bond, well, we just have to work out what the correct answer is here. Are they equally shared between the 2 atoms? Well, no, they're not, because the chlorine is more electronegative, so they're going to be pulled towards the chlorine. Are they completely transferred to the chlorine atom? Well, electronegativity difference is substantial, but certainly not enough to generate an ionic substance. So we expect it to be covalent. C is false based on the same argument. D is the exact right answer. They are unequally shared and they'll be strongly attracted towards the chlorine atom. The average positions of the electrons cannot be determined. Well, that is true, but in this case you can certainly know they are more towards the chlorine than the carbon. So just giving up is not a correct answer. Okay, in this case we're given a Lewis structure of a complicated molecule, in this case aspirin, and we have to work out the bond angles. So some of these are reasonably straightforward. If you look at this carbon atom here, you'll notice that it has 3 electron domains, and so therefore it must be sp2 hybridized, and that of course has a bond angle of 120. This one here, similarly, we have another carbon atom with 3 electron domains, also sp2, also a bond angle of 120. This oxygen atom here, though, doesn't have an octet at the moment, unless you draw in the non-bonding electrons. And when you do so, and you complete the octet on that oxygen, you'll see that it is based on a tetrahedron. And shapes that are based on a tetrahedron have bond angles of 109 degrees. So the correct answer here, then, is D. You're asked to carry out a VSEPR analysis of the molecule BrF5, and so when you do that, and again, just to warn you, I'm not going to do that in its full form. I'm just going to draw the final structure. Oops, that should be a fluorine. So if you don't know how I got there, just work through the notes. You really do need to know how to solve Lewis structures. So the key thing to look for here is it wants to know the number of bonding and non-bonding pairs, and if you count around fluorine, it has 1, 2, 3, 4, 5 bonding pairs and 1 non-bonding. So that's answer B. How many fluorine, bromine, fluorine bond angles are approximately 90 degrees? Well, there's quite a few actually, because you'll notice that in the plane, let me just come back to here, there are 1, 2, 3, 4, but additional to that, there's another 4 90-degree angles between the vertical as drawn here, fluorine atom, and the equatorial ones. There's a total of 8 fluorine, bromine, fluorine bond angles. What is the orbital hybridization? Well, here what you must do is count electron domains, and there are 6 electron domains in this structure, and so you know that you need 6 atomic orbitals hybridized together to form 6 equivalent hybrid atomic orbitals, and so the only case here is sp3d2, so answer E. So which of these radial distribution functions below corresponds to an electron in a 3s orbital? So what does a 3s orbital actually look like? Well, you know it's spherical, but recall that the number of nodes is equal to n minus 1. And so in the case of the 3s orbital, that is equal to 3 minus 1 equals 2. And when you look at these radial distribution functions, remember that all of them are 0 at the nucleus, because it doesn't actually matter how high the electron density is there. The number of electrons tends towards 0, and so if you remember back to the analogy that I made in class with the City of London, how the population density is highest in the middle, but if you look at the exact centre of London, the actual chance of finding someone exactly there tends towards 0. So this is not a node. It sometimes is if there's an angular node, but in the case of an s orbital there are no angular nodes. And so we're just dealing with radial nodes. So what we're looking for is one of these things that has two radial nodes, neither of which are at the nucleus. And the only case here is this one here. So here we have a radial node and another radial node. So the answer here must be D. Why is it easier to remove a 2p electron from an oxygen atom than it is from a nitrogen atom? Well, let's go through this. Oxygen has the highest effective nuclear charge. Well, that's true, but you wouldn't expect it to be make it easier to remove that electron, so that can't be the reason. B is wrong because nitrogen doesn't have the highest effective nuclear charge. Remember, that is just given by Z effective is equal to Z minus S, S being the number of core electrons. It is easier to remove an electron from a doubly occupied orbital because of electron-electron repulsion. So if you think about what the orbital structure Okay, my apologies if I cut out in the middle of this one. It's basically asking why is it easier to remove a 2p electron from an oxygen atom than it is for a nitrogen atom, even though oxygen has a higher Z effective. Well, the reason is because the electron you're removing is from this 2p orbital here, in which it's paired up with another electron. And this necessarily makes it easier to remove because you relieve some electron-electron repulsion. Next question asks you to work out what the electronic configuration of the SN4 plus ion is. Well, the first thing you need to write down is what the full electron configuration is and then remove electrons. So it happens to be in the filling order in the periodic table as you have krypton 5s2 4d10 5p2. And the key thing to remember here is that the electrons that you remove are the ones with the highest principal quantum number first. So you remove the 5s and the 5p electrons first. So you get rid of those and those to leave you with krypton 4d10, and that's why C is the correct answer. Which element has the most negative electron affinity? So electron affinity generally increases as you go from left to right across the periodic table. Neon has a complete shell of electrons, so it's not interested in gaining another one. And so what you're looking for here is the one that's closest to neon, but not neon. So in this case, that would be oxygen. Now, nitrogen actually happens to have a slightly positive electron affinity, and this is because you're trying to pair up that extra electron in a p orbital, so it's a little bit like the opposite of question 17 that we just looked at. Which of these pair of elements is in the wrong order with respect to their relative size? Well, the key thing here to remember is how size changes across the periodic table, and it generally increases towards cesium. So what you're looking for here is a pair of elements that bucks that trend, and the only one here that does it is antimony and tin, because tin is closer to cesium than antimony is. All the rest of them follow that trend. So D is the correct answer. When an electron is removed from an atom, is the resulting ion smaller or larger than the parent atom? So let's go through these. It's always smaller as the electron is removed from the most spatially extended orbital, and there are less electron-electron repulsions. Well, that's actually quite true, so this is fairly straightforward. Answer A is correct. It says usually smaller but stays the same size if the electron is removed from a doubly occupied orbital. Well, you might expect that to be true given that the orbitals are the same extent, but remember the electron-electron repulsion works not only on electrons in the same orbital but ones in different ones as well. There's no size change because the electron's tiny. Oh, that's true, but we're talking about the space at which the electron takes up. Rather than the actual size of the electron. Usually larger, but stays the same size if the electron is removed from doubly occupied orbital. Still wrong. Always larger, definitely not. Okay. Which of these statements about benzene is false? So benzene is clearly one of these molecules that you need to know the name of. Benzene, of course, is hexagonal, and one of its Lewis structures looks like that, and the other Lewis structure looks like that. And so what you're trying to decide here is a few statements, and most of which are true. The carbon-carbon bond lengths are all the same. Well, they are the same because the resonance picture, when you average out these two equally weighted good Lewis structures, you end up with a picture that looks a bit like that, where the bond order all the way around is at 1.5 rather than being 1, 2, 1, 2, 1, 2. It exhibits delocalized bonding. Yep, that's true, as this picture indicates here. You can draw pi bonds in different places. It's a sure sign of delocalized bonding. The carbon-carbon bonds have a bond order of 1.5. Yep, I've already indicated that. 3 resonance structures are required to fully describe the bonding. Well, that's not true. I've managed to describe it with just using 2 of them. And each carbon atom does contribute 1 electron to the pi bonding in benzene. And so that gives you 6 electrons in total in benzene, and you've got 3 pi bonds, so that's consistent also. Which of these statements about hybrid orbitals is false? Mixing 4 atomic orbitals allows the formation of 4 hybrid atomic orbitals. Yes, that's absolutely true. Mixing an s orbital with 2 p orbitals generates 3 identical hybrid orbitals arranged at 120 degrees with respect to another. That's basically the definition of an sp2 orbital. A square pyramidal molecule is hybridized sp3d2, and that again is true because you end up with a structure that looks something like that. You need 6 hybrid atomic orbitals to accommodate those 6 electron domains, so that works well. A linear arrangement of electron domains implies sp hybridization. That is true. Not always, but certainly that is the usual case for a linear arrangement. You can also have, in unusual cases, something that's sp3d hybridized with all the lone pairs in the equatorial plane. But the out and out incorrect one is the last one, because BF3 is suggesting it's sp2 hybridized. If you look at the structure of that, it turns out to be base. It turns out to be T-shaped. And so a T-shaped structure requires an additional 2 electron domains to accommodate these non-bonding electrons. And so it is sp3d hybridized. So that is the false statement there. Methanol can form a hydrogen bond with which one of these substances? So ethane is just a hydrocarbon that I can draw in short form like that. Ethene looks like that. Bromine is that molecule there. Water, again, I expect you to know what water is, and polypropylene is just a chain, a long chain of carbon atoms with to each of which has 2 hydrogens on them. So the only one there that has a bond between hydrogen and either oxygen, nitrogen, or fluorine is this one. So the answer is D, water. The correct name for the compound below is, well, what you need to do is look at this molecule and find the longest chain. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And starting from the end of the first substituent, well, it turns out we've got it right, because the first substituent in this case is at this end of the molecule, this methyl group here. So this is 2-methylhexane. So B is the correct answer. You might think we're being a bit sneaky here by drawing these bonds in here and not there. So if you guessed instead 4-ethyl-2-methylbutane, just try drawing out that molecule in another way and see whether that actually makes any sense. So we're trying to establish that you can correctly identify the backbone of a molecule. Which of the following molecules is or are chiral? So what you're looking for is molecules in which all 4 atoms around the central atom are different. And if you look at this case, we have 2 hydrogens here, so that can't be chiral. This one is chiral because all 4 are different. This one has 2 fluorine atoms, so that's not chiral. And the last one has 4 different groups around. So the only the answer that's correct is D, 2 and 4. next question, which of these diagrams best describe the band structure of magnesium? It's showing the overlap between the s and the p orbitals. So what you have to think about here is remember that bands are just many molecular orbitals packed together, and like any energy level diagram, you start from the bottom and you fill it up in order of energy. So we can rule out some of these just on the basis that the filling is completely bizarre. So you look at B, and the problem with B is we've filled orbitals here that are higher in energy than orbitals that have been left unfilled. So that can't possibly be correct. That same sin has been committed for D and E as well. Energetically, it would be just favourable for these electrons to move down into lower energy orbitals. A and C could possibly be correct. So what is A telling us? A is telling us that this S band is half filled, which implies there's just one S electron. And for magnesium, that is not true. It has two S electrons, so we can rule it out on that basis. And that just leaves us with C. So what happens here is the reason magnesium is a metal is because the S band doesn't completely fill up, because it overlaps slightly with the P band. And so some of the most bonding orbitals of the P band are filled in preference to the most anti-bonding of the S band. So C is the correct answer here. Okay, this final case here, no, it's not a final case, it's an example of enthalpy changes. I happen to know the correct answer here, but just so I'm not actually going to go through the calculation, I'm just going to break it down for you. There are a number of ways of going about doing this. One way, you can just break every bond in the structure and reform every bond in the structure on the other side. So one of the ways of going about this is to say there are 4 NH bonds on this side, there are 2 NN bonds on this side, so there and there, and 1 NN bond on that side. And that goes to a structure where you also have 4 NH bonds over here. You have 1 NN bond, and you have 1 N triple bond. And so you can do some cancelling here. So you can just cancel those out and those out. You cancel out one of the bonds on that side and one of the bonds on that side. So what you're basically ending up comparing is the relative strength of a nitrogen-nitrogen single bond, a nitrogen-nitrogen double bond versus one nitrogen-nitrogen triple bond. And when you do those sums, you come out with C as the answer. So these are numbers you will get directly from your data sheet. The other way you can do it is simply just by inspection. So you'll see here that the NH bonds don't get broken, so you can just ignore them, and you end up breaking a double bond and 2 single bonds to form a triple bond and a single bond on the other side. 29. The compounds bromine and iodine monochloride have the same number of electrons, yet the bromine has a lower melting point than the iodine monochloride. So why is that? Well, both of these in fact are covalently bonded. Bromine of course shares the electrons perfectly. ICl has a slightly different distribution of electrons, but the electronegativity difference is not enough to make them ionic. So B is the correct answer. I and Cl have different electronegativities, so that makes the covalent bond polar. So if we're drawing this molecule, we draw it something like this with a positive charge at that end and the negative charge at the other, the partial positive and negative charges. And so you have a dipole there. And when you have dipoles, you have dipole-dipole forces, and this will add to the attraction of that molecule. Br2, well, it has about the same number of electrons. That would be a very hard thing to judge as to which one would be more polarizable. So we would just guess they're roughly similar. There's no real reason why this should have greater London dispersion forces, because it has the same number of electrons. And finally, bromine experiences no intermolecular forces. Well, that's not true of any substance. Even helium, which is notoriously unwilling to engage in any kind of intermolecular interaction, still experience some intermolecular forces, even though they are very, very weak. So the correct answer there is B. So why is the electron affinity of germanium a larger negative number than for arsenic? Well, that is to do with what we're looking at here. Electron affinity, so they change going from left to right. This is a similar question to one we have already encountered. So in the case of the electronegativities, so I mean these look like they're directly opposed to one another. The electronegativity of arsenic is indeed higher than that of germanium, but you would expect, that being the case, that arsenic should have a higher electron affinity, so that can't be the reason. This is just simply not true. When you add an electron to germanium, it goes into an empty orbital. So remember that germanium's looks something like this. So the next electron you put into it goes into an orbital that is vacant. On the other hand, arsenic has the electronic configuration where this is the S and the degenerate P that looks like that. And so when you try to put an extra electron in, you have to pair it up, and that's unfavorable, so that makes it a little bit lower. So C is the correct answer here. So size is not relevant in this case here. And the effective nuclear charge, again, that's not actually true, because arsenic is further to the right hand side than germanium in the same rows, so you'd expect arsenic to have a higher effective nuclear charge. Which of these statements about nanomaterials is incorrect? Well, nanomaterials do have dimensions in that scale. Their properties do change when the dimensions are in that range. Nano does mean 10 to the minus 9. You can change the size of nanoparticles and give them quite different optical properties. So all of those are correct, and so that leaves this last one. Nanoparticles have continuous molecular orbital bands rather than discrete energy levels. This is certainly true of a solid substance, but nanoparticles are in that intermediate regime between solids, which have bands, and molecules, which have discrete energy levels. And so nanoparticles have discrete energy levels. They're just very close together. Which of these molecules is a saturated hydrocarbon? Well, 2-pentene is So which of these molecules is a saturated hydrocarbon? Well, 2-pentene is this molecule here. Ethine, oh no, I need to add a few more carbon atoms here because we've only got 3 at the moment, so we'll add a 4th and a 5th. Ethine is just a single triple bond. Butyl hexanoate is an ester. 2,2-dimethylbutane. We can draw that structure as first of all a butane. That's 1, 2, 3, 4, and it has 2 methyl groups, so it would look like that. And then finally, so this is an ester, and propanone is, that's also known as acetone. And so we have, so this is a ketone, this is an ester, that's an alkyne, that's an alkene. So the saturated hydrocarbon, that is an alkane, is D. How many different isomers of C3H8O can you draw? Okay, so if we look at this structure here, let's just put down carbon atoms and join them up. So we'll put carbon, 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 oxygen, and then we'll just assign hydrogens to them and just check that we have the right number. And what I'm going to do, just for simplicity's sake, is just draw them as a line. So 1, 2, 3, 4, 5, 6, 7, 8. So we have the right number of hydrogens there. So we can also draw the oxygen in a different position. So if we go C, C, O, C, this is an alcohol, because remember that's a hydrogen. In this case here we have 1, 2, 3, 4, 5, 6, 7, 8, still the right number of hydrogens, but you notice we now have an ether. The last possibility, if you draw the oxygen anywhere else, like if I draw it over here instead, I've just generated this molecule because you can just flop it over and it would be the same one. The one thing we can do is we can draw this one slightly differently. So we can say, okay, we've got a carbon atom and a carbon atom, but I'm going to draw the other carbon atom off there. So you can have 1 hydrogen, 2, 3, 4, 5, 6, 7, 8. So there are 3 isomers in total. So any of the others you draw are actually functionally equivalent to one of those 3 there. So the answer is C. The next question asks how many sp3 hybridized carbon atoms are present in this molecule. So pay attention to the fact that it says carbon. So we're looking for carbons with 4 bonds, remember. So here's one, here's another, here's a third, and that's it, because all the other carbon atoms are sp2 hybridized, because they just have 3 electron domains each. And so 1, 2, 3, answer C. What are the oxygen-containing functional groups in that molecule? So we have this functional group here, which is ROR dashed, which you should know by now is an ether. And this one up here, which is C double bond O OH. So RCOOH is a carboxylic acid. So you're looking for one that contains those 2 things, which just happens to be A. Okay, we're getting towards the end now. Which of these statements about hybridization is correct? The first one is fine. Water is bent because the oxygen atom is sp2 hybridized. Well, let's draw water. Water is HOH, but remember we haven't completed the octet. So we need to give oxygen another 2 pairs of electrons in order to do so. 4 electron domains, it must be sp3 hybridized, not sp2. So presumably all the other statements are correct. And that is right, because so this one here, the bond angles are all 90 degrees in all compounds with an sp3d2 hybridized central atom. Well, just to give you an example, we saw bromine, fluorine, fluorine. We saw this square pyramidal structure before, and while most of the bond angles are 90 degrees, there are some that are 180 between adjacent atoms. Okay. Carbon atoms in benzene, of course, are sp2 hybridized. The carbon atoms in hydrocarbons are always sp3. Well, that's not true, because an alkene or an alkyne can also be a hydrocarbon. The ellipsoidal rods in the picture below best represents molecules in what? Well, let's have a look at these things. We have a whole lot of molecules which are rod-shaped and aligned pointing in one direction but with no other sorting. So remember that if they're roughly in layers like so, we would have a smectic structure. If those layers were then rotated with respect to one another, we'd expect it to be cholesteric. This is clearly not completely disordered, so it's not a liquid. It's clearly not perfectly ordered because it's not a crystalline solid. So that leaves us with nematic. Okay, how many isomers of C4H10O are ketones? Okay, let's have a look at this. So remember that a ketone has a carbon-oxygen double bond in it. It has a carbonyl group. It must have carbon atoms either side of it, like so. So all of our isomers need to have that group in it. And actually it turns out it doesn't matter where you put the next carbon atom, because remember that C4, we need 1, 2, 3, so you need 1 extra carbon atom. It doesn't matter if you put it there and there, you generate the same molecule. So when you come up with this, you'll find that all of your isomers that are ketones must look like that. So there's just one isomer. Okay, that's it. Good luck in your final.